In this video, you will learn about dead fuel moisture and its importance in wildland fire. You will learn 1. What is dead fuel moisture? 2. Why is it important information for fire managers? 3. What is moisture of extinction? 4. What is equilibrium moisture content? 5. What is the time lag concept? 6. How do other factors influence dead fuel moisture content? 1. What is dead fuel moisture? Fuel moisture content of dead vegetation is a measure of the amount of water in a piece of fuel and is expressed as a percentage ranging from about 2% to 30% during the fire season for typical wildland fuels. Dead fuels include all dead plant parts such as litter, duff, fallen logs, as well as cured plants like annual grasses that dry out and lose moisture. This also includes dead vegetation that is still attached to living vegetation and standing dead trees. 2. Why is it important information for fire managers? Dead vegetation is critical in determining fire potential. Unlike live fuel, dead fuel responds solely to ambient environmental conditions and is highly susceptible to daily changes in moisture content levels. Dead fuel cells can absorb water vapor from the air and absorb liquid water in the form of dew or rain. Dead fuel loses water through evaporation when the atmosphere is drier than the fuel. Fine fuels such as grasses, needles, and twigs can react daily, yet larger fuels such as branches and logs will take longer to absorb and lose moisture, especially in the center of the fuel. For fire managers, using dead fuel moisture levels to determine the potential for fire to ignite and spread is critical on wildland and prescribed fires. Fine dead fuel moisture, such as grasses and pine needles, is an important factor in determining fire behavior, including rate of spread, flame lengths, and fire intensity. Generally, the drier the fuels, the faster and hotter the fire will spread. Fire behavior is discussed in another video. Fire and forest managers monitor fuel moisture levels frequently during a fire season to determine the potential for a wildfire to ignite and spread. The Forest Fire Danger Rating System is based partly on dead fuel moisture levels. Prescribed fire managers use fuel moisture levels as a deciding factor of how best to meet burn objectives. This information helps to determine the potential fire behavior and fire effects. If the moisture content is low, the fire can become intense and erratic, and fire effects may be severe. If the moisture content is high, little fuel may be consumed. 3. What is moisture of extinction? At some moisture level, fuel is too wet for fire to spread. This is called the moisture of extinction, and in dead fuels can be between 12 and 30%. This percentage will vary with fuel characteristics such as the size, amount, and arrangement of the fuels on the landscape. In general, fine fuels such as grasses will have a lower moisture of extinction, while in larger size fuels the percentage will be higher. 4. What is the equilibrium moisture content? In a wildfire situation, the lower the EMC, the more fuel is readily available to burn because the fuel is dry and ready to ignite. Dead fuel reaches its equilibrium moisture content, or EMC, when the fuel has reached equilibrium with its environment. However, the equilibrium is dynamic and changes with relative humidity and temperature. For example, with high relative humidity, the water content at which fuel will stop exchanging moisture with the atmosphere, the EMC, is fairly high. In a drier atmosphere, there will be higher evaporative demand for water vapor from the fuel. Thus, the EMC is lower. Temperature also has an effect on EMC. Thus, EMC will decrease as temperature increases. The material or the size of the fuel is also a determining factor of the EMC of that fuel. Next, we will discuss these different fuel size classes with the time lag concept. 5. What is the time lag concept? The time lag principle states that when the environment changes, fuel requires time to wet or dry to approach EMC. A time lag is the amount of time that it takes for a fuel to approach its EMC due to changes in the environment. Moisture gain or loss does not occur at a constant rate, and when conditions change, the fuels will respond quickly at first. The time lag of fine fuels is short because they reach their EMC quickly. To explain further, smaller fuels have a greater surface area to volume ratio than larger fuels, which means it takes less energy and time for smaller fuels to lose moisture. Water near the surface of any fuel can be evaporated fairly easily, but it requires more energy to evaporate water from the center of a fuel, especially in larger size class fuels. Heavy fuels have a much longer time lag and generally will never reach their EMC due to constantly changing conditions. Time lag is related to fuel size. For example, fuels 0 to 1/4 inch in diameter generally approach equilibrium moisture content at a much faster rate than larger fuels. This is why they are called 1-hour fuels. Larger fuels such as 10-hour, 100-hour, and 1,000-hour fuels approach the equilibrium moisture content at progressively slower rates. As you can see, the 1/2 inch sticks gain and lose moisture more quickly than the 12-inch log. The smaller the fuel size, the less time it takes for that fuel to gain or lose moisture. Wildland fuels are heterogeneous across a landscape. The wide variety of fuel sizes and shapes, plus weather changes, make it impossible for an entire fuel complex to be at EMC at the same time. Remember, when fuels get a day of precipitation, they will both gain and lose that moisture at different rates depending on their sizes. This is important information for predicting fire behavior and for assessing the potential effects of a fire. 6. How do other factors influence dead fuel moisture content? Dead fuel moisture is affected by all three legs of the fire environment triangle, with weather as the primary influence. Weather influences atmospheric temperatures and relative humidity, which in turn affect fuel moisture. Shade from clouds or overstory canopy cover can raise fuel moisture levels slightly in 1 and 10-hour fuels. Fuel moisture in those same size fuels can be influenced by wind. Typically, winds during fire season speed evaporation rates and decrease fuel moisture. Topography can affect fuel moisture of all size classes of fuels. South-facing aspects tend to be hotter and drier. Fuels at high elevations have a shorter growing season and generally greater fuel moisture content due to the lower temperatures and higher humidity. Narrow canyons can provide more shade and are cooler than more exposed areas. From this graph, we can see how aspect affects fuel moisture levels. Except for the early morning hours, fuel moistures are lower throughout the day on south slopes than on north slopes in the northern hemisphere. Southwest slopes usually have the lowest afternoon fuel moistures. The properties of the fuel directly influence the fuel moisture content. Compacted fuels, such as a slash pile or dense pine needles, will have slower evaporation rates than fuels that are more loosely arranged. And now, let's review. 1. Dead fuel moisture is the amount of water in a piece of fuel, which typically ranges up to 30% during the fire season and can fluctuate on a daily basis according to the weather and the time of day. 2. Fire managers use this information to help determine the potential for a fire to ignite and spread, as well as potential fire behavior and effects of wildfires and prescribed fires. 3. Moisture of extinction occurs when the moisture level of a fuel is too high for a fire to spread. 4. Dead fuels approach equilibrium moisture content when they can neither lose nor gain moisture, and this can change many times in a given day. 5. A time lag is an indication of the rate a fuel gains or loses moisture due to changes in its environment. Time lag is related to fuel size and is expressed in hours: 1, 10, 100, and 1,000 hour fuels. When the environment is hot and dry, the EMC of all size classes of fuels will be lower, which means that the potential for a fire to ignite and spread is high. 6. Topography, atmospheric conditions, and fuel properties all affect fuel moisture levels.